So the third assignment should be out today. I'll email TAs and they'll make it available online today. Let's see. November 17th, I believe, is when your project, the 4-page project proposals are due. Within this week, early next week, you'll get some feedback from TAs about the projects. What else is missing? I think that's about it, right? So you only have the third assignment. It's going to be out today. It's going to be due in 2 weeks. And the projects, and then you're done. Okay, so today we're going to look at deep Boltzmann machines. And we're going to start looking at the class of unsupervised learning. So far, we've been primarily focusing on supervised learning algorithms, right? Like we've looked at deep networks, convolutional networks, RNN models. A lot of it is really translating from one thing to another thing. But for the rest of the course, we're gonna look at unsupervised learning. If we look at the landscape of unsupervised learning, there are classes of non-probabilistic models that we've already covered, like sparse coding, autoencoders, and such. And then there are classes of probabilistic generative models. And these classes include fully tractable models, like fully observed belief networks. Again, we've seen that example, I believe, last class, right? When we were looking at recurrent neural networks for generating images. And then there's a class of non-tractable models. So in the next few lectures, we're going to be looking at these class of models. So we're going to look at deep Boltzmann machines today. We've looked at RBMs before. We're going to look at variational encoders, Helmholtz machines, and such. And we also looked at deep belief networks, right? So we've covered deep belief networks and restricted Boltzmann machines. But now we're going to look at other sort of deep generative models. And you can think of these models as having explicit density. Right? All of these models are trying to model probability of X one way or another with some approximations. There are also classes of models called generative adversarial networks and moment matching networks. And these models don't necessarily have to model the density. So the density definition of the density there is implicit. And we'll see some examples of that. Now, to just contrast two models. We've covered deep belief network, right, last time when we looked at RBM followed by sigmoid belief network. Today we're going to be looking at deep Boltzmann machine, which is on the model on the right. And the model on the right, if you see, the semantics are different. So the deep Boltzmann machine is an instance of a Markov random field. It's a non-directed graphical model. Whereas deep belief network, it's a hybrid model. And remember, the motivation for deep belief network was this idea of pre-training. And the idea of improving the variational bound. That's how the definition of the model came around. But if you look at deep belief networks are hybrid models. Inference in a deep belief network is actually, like the proper inference, is actually pretty difficult. The reason why is because if I want to figure out what the state of this hidden unit is, remember the notion of the Markov blanket for directed graphical models. It really is going to depend on the children, it's going to depend on the parents, and it's also going to depend on co-parents because of explaining away, right? Is this thing explained away by this feature or that feature? So it's a fairly complicated problems. Typically, you can do greedy pre-training. There is no joint optimization of all layers. There's been some algorithms called up and down algorithms introduced by Jeff Hinton to kind of optimize all the layers jointly, but it's not quite, trying to optimize the overall objective. And when we look at approximate inference, right, when we try to figure out what are the states of the hidden variables, in a deep belief networks, the inference is just feed forward, right? So given the input, you just infer the states of the hidden variables using a neural network. So there is no sort of bottom up and top down feedback. So what we're going to do today is we're going to look at a new class of models called deep Boltzmann machines. We're going to go through math behind these models, and next class we're going to look at some applications of these models. Let me show you an example of this particular deep generative model, So here you're trying to model the probability of the image. And this is the model that has 3,000 hidden variables. It's an older model. You have 784 observed variables, about 2 million parameters that you're training. And what you're trying to do is you're trying to model distribution of these characters. So you have Arabic, you have Cyrillic, you have Sanskrit. And what I'm going to show you is I'm going to show you a model that's actually generating images of Sanskrit. So here you're running Markov chain Monte Carlo, much like you were running MCMC for RBM model. Here you're sampling the states of the hidden variables, and every single configuration basically gives rise to the Sanskrit character. And so if it goes through the whole sort of manifold of Sanskrit characters, this is what it generates, right? So the question is, do these look like Sanskrit characters? Can anybody confirm? Yeah, a few faces are, yeah. I don't know, but it does look like Sanskrit characters, right? So this is, again, one particular model. And again, if you think about what these models are doing, that they're modeling this distribution of a 28 by 28 pixels, which is 784 numbers. And if you look at the space of all possible images, these are binary images that are 2 to the 784 possible configurations. Right, so that space is exponential. It's like the number of images you can generate is more than the number of particles in the universe, right? So you have to resort to some approximation algorithms to be able to train these models, and that's what we're going to cover today. Another example, what you can do is you can do conditional simulation. So you can say, well, given part of the image, can you complete the remaining part? Right, so it kind of works under the constraints of simulating these remaining, and sort of it works through the space of all possible completions, right? As the Markov chain is running, and I think in one of the classes we'll cover Markov chain Monte Carlo method, because I think that these are very heavily used techniques for doing approximate inference in these models. So why is it so difficult? Again, as I mentioned before, you have 28 by 28 image, which is a pretty small image, but it's binary. Then there are 2 to the 784 possible images, right? And so you have to be able to navigate through that space efficiently. Okay, so fully observed model. There's been a lot of work on, and we've seen some of that in last class, where we're basically trying to model the distribution. Think of modeling distribution over all pixel intensities as pick the first pixel, and then look at the conditional probability of the second pixel given the first pixel, and then look at conditional probability of the third pixel given the previous 2 pixels, and so forth. And each condition can be a complicated neural network, and we've seen examples of this bunch of work, if you're interested in, to look at. These are just examples generated by Pixel CNN, which is remarkable, actually. Like, if you look at it, it's pretty impressive what they can do. I think that these models are now state-of-the-art models in terms of density modeling or doing density estimation. RBMs, just as a reminder what they are, maybe I'll just go very quickly over these. You have the joint probability distribution. You have the observed, the conditionals. Right? This is what your homework, you were working in your second homework. There's a Markov random field. Model learning. How do you do a learning? Remember, we looked at the maximum likelihood objective. And if we look at the derivative of the log likelihood with respect to the parameters, we were basically coming up with these 2 expectations. Right? And that's exactly what you were optimizing over in your second homework. This thing was easy to compute, but the second thing is difficult to compute, right? Because this is the expectation of exponentially many configurations. So you have to use contrastive divergence, right? Your friend, where you're kind of trying to basically approximate this expectation by starting at the data, sampling the hidden states, sampling the fake data, and basically saying that's my approximation to this expectation, right? And I think that some of you also tried persistent contrastive divergence, which is kind of like running this Markov chain and trying to get samples from this model, or approximate samples from this model. Because if you can draw samples, approximate samples from this model, you can estimate this expectation using just Monte Carlo approximation, which is exactly what the second homework was about. So the first term is easy to compute, the second term is difficult to compute, and so you have to use Markov chain Monte Carlo, right? And this is known as an approximate maximum likelihood learning. Right? So that was your homework 1. Now, let's look at deep Boltzmann machines. And the idea is very similar to what we've done with deep belief networks, right? We're going to introduce a second layer of hidden variables. So you have higher level features, combination of edges. And the goal, much like in deep belief networks, is to learn simpler representations and compose them into more complex ones. Okay? The semantics of this model is very different from the semantics of deep belief networks, right? Because this is an undirected graphical model. So if I look at the formulation for this model, the mathematical formulation, this is an instance of a deep Boltzmann machine. You have model parameters, W1, W2, W3 are the model parameters. All connections in this model are undirected. So this is known as a Markov random field with layers of hidden variables. Okay? And you're basically introducing dependencies between hidden variables. And compared to what happened before is that we have these 2 additional terms. Right? If I just look at the first term, it's exactly what RBMs are doing. And now we have these 2 additional terms, and these 2 additional terms are modeling dependencies between H1 and H2, and H2 and H3. Right? So for those of you who've taken a graphical model class, this is nothing more than a Markov random field with just layers of hidden variables. That's all that is. There is also one interesting property for this model, which doesn't exist in deep belief networks, which is the notion of conditional independence and Markov blanket, right? So here, if I say, what is the state of this variable? The state of this variable really depends on the states of the variables below and the states of the variables above, right? So there is very natural notion of bottom up and top down, right? And this sort of has 2 implications. On one hand, I think these models can deal with uncertainty much better, right? And this has to do with the fact that if I see some visual input, and traditional models like a feed-forward networks, like convolutional networks, there was a model called HMax, which is another model of deep belief networks. These models, they all do feed-forward inference. So given an image, they extract features, and extract features, and extract features, then you classify, right? What happens with these models is that you have to resort to some more approximate inference, which is basically say, well, given the features, I extract some features, layer 1 features. But the state of these layer 1 features really depend on, what the layer 2 says. And so you start propagating uncertainty up and down in the model, up until you settle to some steady state, right? So you sort of have to, have an agreement of what this layer thinks and what this top layer thinks. And this has some nice properties. People who are working in computer vision domains usually basically look at larger contexts. Like if I look at one piece and I'm not sure what this is, maybe I can abstract it, look at the high level information, and then come back and really tell you what that is. So that's a nice property of the model. You can also define conditional probability distributions, much like you define them in restricted Boltzmann machines. Right? So one thing in this model is that you can't really compute the conditional probability of H1, H2, and H3. Right? Because condition on observed data, this whole thing here becomes a complex MRF. But at the same time, you have conditionals. So here you can say, well, the conditional probability of layer 3 really depends on layer 2. The conditional probability of layer 2 depends on layer 1 and layer 3. Conditional probability of layer 1 depends on layer 2 and the input, right? So you have these nice block alternating Gibbs sampling updates that you can do in order to be able to sample approximately from these conditionals. So in other words, to do inference in this model, you sort of have to do some form of sampling. And I think that my PowerPoint crashed again. Let's just see. Yeah. Right. So if you look at what this model is trying to do, right? Given the data, there's some inference that we have to do to get to some steady state. If we look at neural networks, traditional neural networks, what they do is that given the input, you just propagate information upwards, and then you classify or you do some kind of decision at the top. If you look at deep belief networks, right? Deep belief networks are these hybrid models. But when I actually do inference in deep belief networks, they basically are just exactly the same as traditional neural networks. So inference in these models is just a feed forward. Whereas inference in this model in deep Boltzmann machines is you have to kind of do up and down algorithm here. And again, it has two implications. On one hand, it can deal better with uncertainty. On the other hand, as we'll see, it's computationally much more, intensive, right? Because you have to figure out how do you settle to some steady state so that everyone is in agreement. So it has pluses and minuses. Now, let's look at maximum likelihood learning. Maximum likelihood learning, again, just as a reminder, has this form, right? It's expected sufficient statistic driven by the data versus expected sufficient statistic driven by the model. And that's exactly what the learning rule you had for RBMs. And this is the same learning rule for any type of undirected graphical model. So if you ever worked with conditional random fields, if you've heard about CRFs, Markov random fields, MRFs, factor graphs, all of these are instances of undirected graphs, and that's the learning rule. You're essentially trying to match expected sufficient statistics in data versus expected sufficient statistics in the model. And again, the intuition here is given the data, what correlations do I see in the data? That's essentially what the first term is doing. The second term is basically saying, what does model believe those correlations should be? And you're matching the two. The problem is that both of these expectations are now intractable. So you have to do some approximation here. So both approximations are intractable. And the reason why is, again, to compute the data-dependent expectations, you have to be able to compute the conditionals. In RBMs, we could compute this conditional because we only had one layer, right? So now we cannot really compute these conditionals because the states of the layer 1 really also depends on the states of the layer 2, right? And we don't know what the states of the layer 2 is, right? So that kind of comes back to this problem. Now, the other thing to think about these models is, let's say I have the data. And let's say I get to observe these handwritten characters, right? The first thing I need to do is I need to assign some probability to these examples, right? Because they are probable. Like they should carry some probability because I see them in the real world. And that's exactly what the first term is trying to do, essentially. It's trying to look at the data and trying to raise the probability of observed data. On the other hand, if I look at this image, which is some random image, I want the probability of this image to be very small. In fact, I want it to be exponentially small. And that's the role of the second expectation, right? Because the second expectation here is really the derivative of the log of the partition function. And so partition function is z, the normalizing constant. Partition function is actually carries it's a very important mathematical object. If you ever want to look at statistics and MCMC methods or variational methods, pretty much all of them are trying to deal with exponential sums or trying to deal with estimating log of the partition function or estimating the gradients of the log of the partition function, because that's what you need to do learning. So these are, estimating partition functions is kind of like a huge subfield within machine learning and statistics as well. So what we're going to do is we're going to use variational inference to estimate the data-dependent expectations, and then we're going to use stochastic approximation, which is Markov chain Monte Carlo-based inference, to estimate the second expectations. I think that what I'm going to do is I'm going to walk you through the mathematics behind these models. I'm not going to be testing you on this, obviously, but hopefully I'll give you some intuitions about both variational inference and stochastic approximation. Just to say that variational inference for this model takes, I think, about 7 lines of Python code. And Markov chain Monte Carlo inference also takes about 9 lines of Python code. So these are fairly simple implementation algorithms, but mathematically they are kind of not very trivial. So let me give you an intuition of what these algorithms are doing, and then we're going to look at some details. So there's been a lot of work on trying to learn Boltzmann machines over the last 20 years. Like if you look at this, and I'm not really doing justice listing them all. People were trying to figure out how can we do learning in these models. And the problem is that if you look at a lot of different applications, real-world applications, you actually have to deal with thousands of hidden variables. And with millions, you have to deal with millions of parameters. And many of the previous approaches were not very successful for learning in general Boltzmann machines with hidden variables. So if you actually look at the literature, there are algorithms based on contrastive divergence. Contrastive divergence works well if you have one layer of hidden variables. There is something that's called score matching. There is something that's called pseudo-likelihood estimation. There is something that's called composite likelihood estimation, Markov chain Monte Carlo MLE estimation. There's been some work on piecewise learning, where you basically take an arbitrary graphical model, decompose into pieces, and then learn pieces, and then pull them together. So there is a rich literature. Composite likelihoods is again like a big subfield in statistical in statistics and statistical decision making. Pseudo likelihood is an example of a composite likelihood. So if you're interested, there is a whole body of work in that space. But none of them really can handle many layers of hidden variables, right? Because information has to propagate up and down in the network. So let me show you the intuition of what we're going to be doing. Given the data, the first thing we need to do is we need to infer what are the states of the hidden variables given the data, right? Think of it as follows. If I give you the data and you have to classify what that is, let's say, I want to be able to figure out what are the states of, what are the features I'm seeing in layer 3? What are the features, distributional features I'm seeing in layer 2 or layer 1, right? So that I can actually take these features and classify what I'm seeing. So inference is important, and with inference, you know, to estimate, to do maximum likelihood estimation, we need to do inference. On the other hand, I can simulate from the model, right? So I can run Gibbs sampling algorithm, just sample from the conditionals, and I can simulate the data. Now let's say my simulation looks like this. Okay, so I sample from the model, this is what the data looks like. Now I can estimate the data-dependent expectations based on the real data, and I can estimate the data-independent expectations, right, based on these samples from the model. Much like what you were doing with RBMs, I can sample from the model, and I'm trying to match the two, right? And again, the intuition you should have is that what the maximum likelihood is essentially trying to do is it's essentially trying to look at the data distribution, and it's trying to look at the distribution of what the model believes the data should look like, and you're trying to make this look more like this. That's effectively what you're trying to do. Think of it as you're simulating from the model, you get some distribution, you look at the real data distribution and say, well, these two distributions are different. How can I figure out the way to make them be similar, basically? That's essentially what the algorithm is trying to do, right? Because you're building the density estimation model. Now, if I look at this space, the space of samples, the space of H and V, this space is very multimodal. Imagine the space of all possible characters you can generate, right? Or the space of all possible images. There are multiple modes. I can generate all kinds of characters. I can generate all kinds of digits or all kinds of binary images, right? So there are lots of modes in this distribution. It's a very complicated model. It's a very complicated distribution to fit. On the other hand, given the input, right, if I show you what that is and do the slice through that, in that particular just a pictorial representation, I'd expect this posterior to be mostly unimodal, right? There might be some uncertainty about, like, do I see a pixel here or here? Maybe this, some uncertainty over here. But it's not like I look at this image and I say, well, it could be a car or it could be a flower, right? There's like two completely different explanations of what I'm seeing here. There are examples where this is the case. Like one example, if I give you an H and I rotate it 45 degrees, is it an H or is it an I? Right? It could be H, it could be I, right? Depending on how you drew it. So there could be some uncertainty, but generally this posterior is typically unimodal. Might have a couple of modes, but typically it has a single mode in the posterior, right? Whereas this distribution here, the space of all possible characters, it's a very complicated, very multimodal space. So what we're going to do is we're going to do data-dependent expectations. We're going to be using variational inference. Something is called mean field theory. And for data-independent, we're going to be using stochastic approximation, which is Markov chain Monte Carlo-based estimation. So let me show you what these two things are. First of all, how do you sample from the model? Right, I've shown you sampling from a Boltzmann machine. The way you sample from the model is you initialize randomly the states of, let's say, this two-layer RBM. You initialize V and H randomly. You sample the states of the hidden layer 1, just looking at the logistic function of what's coming from above, what's coming from below, much like what you've done with your second assignment. And then you sample again observed variables and hidden variables and so forth, right? So this is procedure. It's fairly efficient. You're just sampling in parallel. You can also sample V and H2 in parallel because they're independent, conditional on H1. So you're just running this GIP sampling in parallel and so forth, right? And now you get a sample from the model. So you get a sample from the model, then you have some notion of what the model believes the data should look like, or the sample should look like. So let's look at the Markov chain-based approximation. So how do we estimate the data-independent sufficient statistics? The way that we do it is the following. We're going to be updating parameters of the model and the states sequentially. Okay? So we're going to generate a sample by running a Markov chain, GIP sampling, much like what you were doing in your second homework assignment, right? So sampling here is just sample the states of the hiddens, invisibles, hiddens, invisibles, maybe for a few steps. This is known by simulating from a Markov chain that leaves peak data sub T invariant, which basically means that you're running a proper GIP sampling or Metropolis-Hastings algorithm or any other version. There are a bunch of things you can do here. But you're sampling from this, and then you update the parameters of the model by replacing this intractable expectation that you can't really compute by essentially using samples from the model, right? With the point estimate there, the point estimate is the sample from the model. In practice, you simulate several Markov chains in parallel, right? So that's the algorithm. You're just sampling from the model, you're taking the averages, and that's your approximation to this expectation. Okay? Very simple. Yes?
So doesn't the state of H2 also depend on the state of H3?
Yeah. If you have another layer, you would basically sample H2 given H3 and H1, and then you sample H3 given H2.
So how does that work?
It's exactly the same algorithm, same procedure. You always sample odd layers given even layers, and then you sample even layers given odd layers. Yeah, you initialize everything at random. This procedure was also developed by Laura Yanis back in '89, this particular algorithm. And it's interesting because it works remarkably well in practice, but unfortunately he published into the journal, in a French journal, and the article was in French, so nobody knew about it up until, and people were developing contrastive divergence and then persistent contrastive divergence and MCMC MLE estimators. Basically, it's his algorithm back in '89. So this was, he basically developed a version of this algorithm back in '89. And it's, GIP sampling was invented in '86, I believe. And he developed it in '89. And so, okay, so now, so what you can do is you can do the following. If you look at the learning rule, right, let's leave the first expectation apart. This is expectation with respect to the data distribution. Let's say we can compute that. And now we can update the parameters by basically replacing the second expectation by an average of your samples, right? You run your Markov chain, you're getting samples, you're taking the average over those. So now the first part is variational, the second part is MCMC, right? We're going to talk about variational. But the way to think about and do analysis of this algorithm is the following. This is the true gradient. This is what I want to compute, right? The second one is you can think of it as a perturbation term. It really is looking how much your Markov chain samples are off compared to the true expectation, right? If the noise term is 0, then you get the true gradient, right? Because you have a perfect approximation. And what you have is you have something that's called almost sure convergence guarantees as the learning rate goes to 0. So the idea here is that, at least in theory, is that as your Markov chain, as your learning rate becomes sufficiently small compared to the mixing rate of the Markov chain, your Markov chain will keep up. And samples that you generate from Markov chain are going to be samples from the true model, in which case this perturbation term will effectively go to 0. So there is some theory that you have almost sure convergence guarantees. Of course, in high-dimensional problems, your landscape, probability landscape, is highly multimodal. So it's in theory it works. In practice, it's very hard, and there is a lot of different advances. I mean, there's a lot of different fixes that you can do. One thing you can think of is that the transition operator, the Gibbs sampling, can be any valid transition operator. So there's a whole bunch of literature and statistics on something that's called tempered transition, parallel simulated tempering. There's new, different ways of being able to sample the space more efficiently. And there's also a very nice connection to the theory of stochastic approximation, something that's called adaptive Markov chain Monte Carlo methods. So for those of you who are interested in that field, there is a whole body of work on trying to figure out how can I design my transition operators, which don't really have to be simple Gibbs operators, but more advanced operators that allow me to jump between multiple modes in my distribution. And so having more advanced sampling algorithms allow you to build much better generative models. And it's generally the case for a lot of different algorithms in machine learning. Particularly when you're trying to estimate expectations, or you're trying to compute partition functions and so forth. Okay, now this gives us this. It's very simple in practice. Again, you just run your sampler and you just estimate. There's nothing else that you can do here except for trying to come up with more advanced sampling techniques. Yes?
So you mentioned the transition operator here. So in Gibbs sampling, we're just initializing with our random values or something. Is that why we're taking multiple samples here instead of
That's right.
point estimate? And with a different transition operator, you don't do similar because you're
So different transition operators, like for example, if you look at parallel tempering, the simulated, in parallel tempering, you're basically running multiple chains at different temperature levels, and you're kind of mixing between them. The hope is that it's easy for you to jump from image of a 3 to image of a 9. Because if you think about Gibbs sampling kind of just slowly moves from 3 to 9. And maybe it will never reach 9, right? Because the images are so different. But these other techniques allow you to design valid operators that allow you to jump between modes more efficiently. If you can jump between modes more efficiently, you can explore the space more efficiently. You can explore the space more efficiently, your learning improves. So there's been a few papers on basically coming up with these techniques that allow you to train these models more efficiently. Let's look at the variational inference. What is the variational inference? So the idea behind variational inference has been, it's been around for quite some time, but in the context of Boltzmann machines, the idea of variational inference is to approximate your intractable distribution, P of H given V, with a simple tractable distribution Q. And we're going to be parameterizing this distribution by parameters mu. Okay? So think of simple tractable distribution as like a Gaussian distribution, for example. Or think of Q distribution as a fully factorized distribution. Remember when we looked at graphical models, we basically said the simplest possible distribution is a fully factorized distribution, right? It's like independent per dimension. It's like having a Boltzmann machine with no connections, only biases for each unit, right? So this is a simple distribution to fit, right? They're all independent of each other. So what I can do is I can do the following. I can say, well, the log probability of the data, and we've seen this before, I believe, once, but let's revisit this. The log probability of the data, I can write it as a log of the sum, right? I sum up the states of the hidden variables. What I can do then is I can divide and multiply by my approximate distribution Q. And then I can basically put the log inside by the concavity of the log function. Now, you might ask, so what does this give me? Why is this easy to optimize than this? Right? Well, let's actually plug in the definition of P of H and V. Right? What I can do is I can basically say it's log of unnormalized distribution. And remember, what is log unnormalized distribution? It's just this thing here, what was in my exponent. Now I have minus log of the partition function plus what's called the entropy of the Q distribution. And something magically happens here. If I want to say, well, can I optimize this objective with respect to parameters mu? I don't really need to worry about this log partition function. This log partition function is something that I can't compute because it requires exponential sum. And now, all of a sudden, by looking at the variational bound, I can formulate the problem where I don't really need to worry about partition functions because it doesn't really matter what this is. It's just a constant. So it falls out of the equation. This is known as a variational bound. And it turns out that I can optimize this bound with respect to Q. Right? And what does this mean? That basically means I'm trying to say, find me the distribution Q having a specific parameterization mu such that this bound is as tight as possible. And that's the idea behind variation approximation. You're kind of looking at the family of distributions parameterized by Q such that it's as close as possible to P in terms of pushing up on the lower bound. And that's exactly what was happening with deep belief networks. Deep belief networks, they were basically modeling the prior here so as to push the variational bound up. You can also write it down as a log probability of the data, which is what you're trying to optimize, minus the Kullback line that diverges between Q and P. So Q is your approximation to the posterior, and P is the true posterior. So you can think of it as basically saying, how can I do optimization in such a way that I'm actually improving my log probability of the data, but at the same time, my Q should be close to the posterior as well. So that's what the variational learning is doing. But the importance for undirected graphical models is that we don't need to worry about partition function, right? So here you're minimizing KL divergence between approximating and the true distribution with respect to the variational parameters mu. Now, this is variational bound. We can choose a fully factorized distribution. So I can say that my posterior is going to be a product of these conditionals, and they're all going to be independent. So it's like saying I'm going to break all the links in my deep Boltzmann machine model. Again, it's just as an approximation. And the variational inference, you're maximizing the low bound with respect to the variational parameters mu. It turns out that if you plug this into the definition of the variational bound and you optimize, it comes down to basically optimizing, you have a nonlinear fixed point equations. So it's, and it's interesting, the variational has it's an interesting form. These nonlinear fixed point equations are exactly the same equations as what you would do with Gibbs sampling, except for you don't sample. You just compute probabilities, and you just compute probabilities, and then you settle to some state, and you say that's your approximation. The other thing about variational inference, and mean field approximation in particular, mean field approximation, you can show that what it does is it captures a single mode in the posterior. Because your approximation is fully factorized. You can only capture a single mode in the posterior. at the assumption that the posteriors in these models unimodal, variational inference is very efficient at finding this mode. So it's like finding a single explanation to what's going on in the data in a posterior. If your posteriors have multiple modes, it will ignore one mode and will just capture the other mode. So what that means is that we can actually run the fixed point equations here. Typically, you run it for a few steps, 5 or 6 steps, and they converge. And that gives you some pretty good approximation to the posterior. The mean field approximation is not just useful for Boltzmann machines. It's used a lot in other kinds of graphical models, like, if you've heard about latent Dirichlet allocation models or any kind of Bayesian models, this is heavily used as a variation approximation to the posterior. Pretty much the same ideas go through as well. So this is not something specific to this class of models. This particular formulation of mean field is applicable to all classes of models where you can't really, your posterior is very complicated, so you have to resort to some approximation, and mean field approximation is one way of doing it. There is no stochasticity, there is no sampling, you just run a fixed point equations, and every single update here optimizes the variational bound. So your bound sort of goes up after every single update. So if you look at the overall algorithm, you can think of it as follows. There's an inference step. You're maximizing the low bound with respect to variational parameters. Think of it as like an E step in EM algorithm, right? And then there is kind of like MCMC step or the M step where you're applying stochastic approximation to update model parameters. So you're updating parameters of the model by collecting statistics from E step and variational step and MCMC step. Okay? Fast inference. So if you're using mean field, it takes a fraction of a second to do the inference. Learning can scale to millions of examples because your Markov chain Monte Carlo can be run in parallel. You don't really need to, and you can use stochastic gradient descent. So the model can be scaled to training on lots of examples. So the question is, if we apply this algorithm, how good of a model you can train? And some of you might have seen this, but what I'm going to do is I'm going to show you 2 panels. On one panel, you'll see the real data. On another panel, you'll see simulated data. And you have to tell me which one is which. So these are handwritten characters. You're modeling handwritten characters. How many of you think this was simulated, this was real? Raise your hands. A few, okay. What about the other way around? A few, okay, good. So it's like 50-50, great. If you look at the data itself, you'll start seeing that this is simulated and this is real, right? I learned this trick from neuroscientists. If I show you these pictures fast enough, you won't see the difference, right? If you actually start looking at them carefully, you'll start seeing the differences. One thing to note is that the real data is much more diverse than the simulated data. Right? There are more handwritten characters. And this has to do with Markov chain Monte Carlo method not being able to explore this space sufficiently, so it really is, optimization issue at this stage. But it does capture the kind of the high-level structure of what handwritten characters should look like, right? And you can see this is not a very trivial modeling task to model what the handwritten character should look like. These are the examples of MNIST handwritten digits. So here, how many of you think that this is real and this is fake? The other way around, this is fake, this is real? A few? Why do you think this is fake? 0. So I promise I didn't put the 0 just to confuse people. So this is real, and this is fake, right? So here, if you actually look at some of the digits, like this one, you'll start seeing that there are pixels missing not quite the right places. You will start seeing that there are some examples, so like this image of a 2. There's a lot of missing ink here. You can also use these models to do handwritten character recognition or optical character recognition and so forth. So this is just to show that these models can generalize and do if you're interested in classification tasks. So here you're extracting high-level features and then you're building a classifier on top of the high-level features to see how well they can do. You can also model the 3D objects. So again, this is without using any convolutions, any sort of prior knowledge about images. And you can see that it's not quite as perfect because it's much harder to generate 3D objects. And you can also see that here it doesn't quite get the right balance between different objects. So it generates donkeys and elephants. There's only one donkey and one elephant, but it generates a lot of people with guns, right? Like if you look at here, 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 and here, and here. Like these are sort of like toy soldiers, but it doesn't quite get donkeys and elephants. So the balance, the class proportions for different classes is not quite well balanced. But at the same time, you can also do things like look at the recognition accuracy for these models. You can also do pattern completion. Given half of the image, you can complete the remaining half, right? So these are the examples. So for example, this image of a cowboy, the model has never seen images of this particular cowboy. It's seen images of other soldiers, but not this one. And so it's able to figure out that given half of the person, it should complete, the leg and the arm and such. Or given the airplane, it should complete, the other wing and stuff like that. So it's capturing some structure in images and be able to do pattern completion. So these kinds of models, you can think of them as learning hierarchical structure and features. You're learning edges, combination of edges, and so forth. You have fast inference. Learning can scale to millions of examples. Let me show you one example. There was a paper at 2012. Let me see if I can get this running of using something that's called shape Boltzmann machine. What they were doing is they were basically saying, well, can we put the priors on the shapes of objects? And if we can form the prior, the correct prior, this was done, I guess, at Microsoft Research, if you can put the correct priors, then it can really help us improve segmentation, for example, of objects. The shape Boltzmann machine was kind of like a two-layer deep Boltzmann machine. Let me show you examples of this. So here's an example where they basically, it's a conditional simulation, right? So they masked part of it and basically said, well, generate me. So it generates different shapes, conditional on other pixel intensities, right? And then they can do interesting things like, so they're generating shapes of horses. So you can see the horses now can like move its legs and such. Right, and again, these are samples by generating from the conditionals. That's an interesting one. So it's kind of forcing under this constraint to generate horses. That's an interesting one. So it generates horses with this leg, right? So because you're basically saying there should be some ink in there. They also were generating, and these are 64 by 64 images. So these are quite, large images. And they're generating, they were generating a whole bunch of different shapes. They're just showing examples of horses and motorcycles. So here, again, they're forcing it to say, well, this should be part of the motorcycle, right? So it tries to generate the shape of the motorcycle consistent with these constraints. You can actually go, I think they have a tool to play with it. And so now it's generating motorcycles under this constraint. So obviously you can see that. And again, they've shown that they can use this for improving segmentation. Because in computer vision, that's a fairly big So now they're generating motorcycles, you know, that are kind of tilted, right? Which is kind of neat, right? This is something that, yeah, was very impressive to, I think it was very impressive to a lot of people because being able to generate the shapes, coherent shapes, and also shapes under constraints is pretty difficult task. And being able to actually generate, you know, realistic ones is pretty difficult. Yeah. Yes, question?
Okay, so in the demo of the model demo, so we have most part of the shape. How does the model know that the left one is front wheel? Typically, the back wheel.
No, I think that most of the motorcycles were like, this is front, this is the back. That's the data. The data that we're training on. But the important thing is, again, what you can do, what they've done is they put this as a prior for segmentation, basically saying, well, if I'm trying to do this segmentation, and I'm saying, this is my segmented motorcycle, they put the prior in and saying, is it consistent with the shape prior? Because if it's not consistent with the shape prior, then you might want to revise your segmentation. So it's kind of like a composite model, which I think is a very powerful model, because sometimes you look at these segmentation algorithms, and you have a horse that's standing near the tree. And the horse's leg kind of like look like a tree. And what the segmentation algorithms do, they basically like segment the horse without legs. So now you have a horse without legs. Now, which is reasonable, because the segmentation algorithm, they look at local structure and they say, well, this is a tree, it's part of the tree, right? And so now you have a horse without legs. The horse without legs, according to this particular model, will have 0 probability, right? Like there are no horses without legs. That just doesn't make much sense. So this prior will force the model to say, no, there should be legs here. And so the segmentation algorithm would basically, the score from the segmentation algorithm will say, yeah, okay, there's some penalty because I really think it's a tree. But if my prior says there should really be legs here, then I'm just going to segment this out and say, okay, this is my best explanation, right? And this is how people work, right? When you look at the image, if you see half of the horse and the remaining half of the horse is like merged together with a tree, you wouldn't say, well, like that's a horse and that's a tree. So it's like half of the horse and then it's a tree, right? To your prior, it wouldn't make any sense, right? You basically can complete yourself, and so now horses should have legs, right? Because they can't just be flying around without legs. And so that's exactly what this prior is doing. And it was able to improve on these kinds of tasks by substantial margin. There was another thing that's, if you're interested in there was a paper, I guess, back in 2012 on hallucinations in Charles Bonnet syndrome induced by homeostasis. So what they've done is they kind of looked at people who are blind. I think they were basically trying to study what blind people are visualizing. And they were able to show some connections between what people are hallucinating and what these deep Boltzmann machines are hallucinating. Which is kind of an interesting paper if you are interested in looking at. There's certain syndromes that they were uncovering. Specifically, the deep Boltzmann machines were modeling something was similar to what people would actually be consistent with how people would generate these images. Okay, so let's stop today. Next class on Monday, we're going to finish the Boltzmann machine. Next class, we're going to look at more applications rather than the definitions and the mathematics of these models, and we're mostly going to look at some of the applications of these models, right? And then we're going to jump back into variational autoencoders, which is going to be a little bit more, again, mathematically technical. Okay.